Good morning. This is Sir Mike, your teacher in differential equations. So this morning we're going to look into one of the applications of first order linear differential equations, and that's on Newton's law of cooling. So for the objectives of today's lesson, first we should be able to derive the formula of Newton's law of cooling using first order linear differential equations. And second one, should be able to use the formula in solving problems involving Newton's law of cooling. The first thing that we need to do is to recall the form of first order linear differential equation, because definitely we'll be using this first order linear differential equations in solving or in deriving the equation that we'll be using Newton's law of cooling. So recall that a first order linear differential equation is expressed in terms of this equation. We have dy over dx plus p of xy is equal to q of x. Now, let's define first Newton's law of cooling. So it says that the rate of change of a temperature of an object is directly proportional to the difference of the temperature of the object at a particular time and its ambient temperature. When we speak of an ambient temperature, it means to say that we are referring to the temperature of the environment or the temperature of the surroundings. So in terms of an equation, we will be using this differential equation. We have dt, capital letter T, referring to the temperature with respect to time t. And this is equal to negative k times the quantity of t minus t sub s. So we have here negative k because, of course, the temperature of the object here is being lowered. Okay, now we're going to define the variables or the symbols that we'll be using in this equation. So we have here dt with respect to time t. So we are referring here to the rate of change in the temperature of the object. And we will also be needing negative k, and it's included in the equation. So this is the constant of proportionality. And then capital letter T, we are referring to the temperature of the object at a particular moment or time. And then we have your T sub S, it's the temperature of the surroundings. Okay, so using that equation, we're going to derive the second formula, or the formula that we'll be using in solving problems involving Newton's law of cooling. So we have here dt with respect to time t, and this is equal to negative k times the quantity of t minus t sub s. This is the, as I mentioned a while ago, this is the equivalent of, the equation equivalent of the definition of Newton's law of cooling. So the first thing that we need to do here in this differential equation is to distribute negative k to the terms inside the parentheses. So we'll be having derivative of the temperature with respect to time t, and this is equal to negative kt plus k t sub s. Then next is we transpose negative kt to the other side of the equation. So we'll be having dt with respect to time t plus kt, and what is left on the right side of the equation is your k t sub s. And recall that in solving a first order linear differential equation, we are actually solving for p sub x. We're looking for p sub x and your q of x. And your p sub x is used in solving the integrating factor. But since here in this Newton's law of cooling, we will be using the symbol for the temperature and time t. So if we compare the first order linear differential equation that we'll be using here in this topic, your y is equivalent to your time, your temperature t, and your x is the independent variable, and it's equivalent to small letter t referring to time. So we can actually change your p of x with p of t. Okay, and based on this equation, our p of t is k. Okay, that's the expression beside your dependent variable. which is the temperature. Okay, and then you're aware that the expression found on the right side of the equation is your q of x, but in this lesson we are referring to that expression as your q sub t, or q of t rather. Okay, and this is equal to k t sub s. And the first thing that we need to do, just like in solving a first order linear differential equation, is to look for the integrating factor. So the integrating factor I of t, this time it's not I of x, but it's I of t. And this is equal to e raised to the integral of k dt. Since your k here is constant, we can factor out your constant k. So the integrating factor therefore is e raised to k times the integral of dt. And you're aware that the integral of dt is t. Therefore, our integrating factor is now e raised to kt. Okay, so you recall the process of solving a first order linear differential equation. We need to factor or to multiply the integrating factor to both sides of the equation in order for us to solve the first order differential equation. So here, we were going to do the same. Okay, notice that I have written here our original process, okay, of finding the general solution of a first order linear differential equation. So we're multiplying your integrating factor I of x with your dependent variable y, and then you get the derivative. Okay, and this is q of x times I of x. But since we are using different symbols here, and our integrating factor in this Newton's law of cooling is e raised to kt, we will be multiplying your e raised to kt to your t with respect to time t plus kt, and this is equal to e raised to kt, that's the integrating factor, times q of t, that's k t sub s. Okay, and here, if we distribute your integrating factor to the terms inside this parenthesis, this can be expressed as the derivative of the product of the integrating factor e raised to kt times the temperature T. Okay, and that's equal to e raised to kt times k times T sub s, the temperature of the surroundings. Then after that, we can take the integral of both sides. And notice here that your k t sub s is constant. So here, in this part of our derivation, we can factor out your k t sub s, the constant of proportionality times the temperature of the surroundings. Well, of course, you'll be needing the integral of e raised to kt dt. Okay, so you take the integral of the derivative of e raised to kt times the temperature. So that's actually equal to e raised to kt times t. But here in the right side of the equation, there's a need for you to apply substitution. You cannot just get right away the integral of e raised to kt dt. So what we need to do is to let u be equal to our kt, and you take the derivative of both sides. You have du, and this is equal to kdt. And in the equation, we are only needing an expression that can be substituted with dt. So we divide both sides of the equation by k. So our dt will now then be equal to your du over k. Now, we substitute the expressions to the differential equation. So we have here, okay, you take the integral of the quantity of e raised to kt times the temperature T prime, and this is equal to your kt sub s times the integral of e. Your kt here is replaced with u, and of course your dt is d all over k, but since 1 over k is constant, we can factor that out. So what is left here is your e raised to u times du, the integral of e raised to u times du. Here, you notice that you can cancel out your k, the constant of proportionality. Therefore, what is left here is of course, your T sub s times the quantity of the integral of e raised to u. So the integral of e raised to u du is e raised to u plus c. But we replace your u with the original expression kt. So we have here, since the integral of the derivative of the product of e raised to kt times the temperature T is equal to e raised to kt times capital letter T. This is equal to your T sub s, because your k is being cancelled out, times the quantity of e raised to kt plus c. Now, we distribute your T sub s to the terms inside the parentheses. So we'll be having this equation, e raised to kt times temperature T, and this is equal to your T sub s, e raised to kt, and then you have the product of T sub s and c. So that's T sub s times c. But your T sub s times c can be equated to another constant, and at this point we're going to make use of capital letter C to replace your T sub s times small letter c, which is constant. Okay, so we now have your e raised to kt times t, and this is equal to T sub s e raised to kt plus the equivalent of your T sub s times c, that is capital letter C. And then after that, we divide both sides of the equation by e raised to kt to solve the temperature T. So you have here T. You can cancel out your e raised to kt in the numerator and e raised to kt in the denominator. And on the other side of the equation, you can also cancel out your e raised to kt in the numerator and e raised to kt in the denominator. So you have your T sub s. What remains is your T sub s. Then on the other side, okay, the next expression, so we have plus c over e raised to kt, but you can actually write your e raised to kt in the numerator. But this time you need to change the sign of your kt. So we have here ce raised to negative kt. Therefore, our formula for the Newton's law of cooling, an alternate formula for Newton's law of cooling, is T, the temperature of the object at a particular time, and that's equal to your T sub S, the temperature of the surroundings, plus C, E raised to negative KT. Now take note of this formula, because we will be using this formula in the solving the problem that follows. Okay, now we look at the application. So for example, here, a lasagna is taken out of the oven, so with an ideal internal temperature of 165 degrees Fahrenheit, and is placed into a 35-degree Fahrenheit refrigerator. And after 10 minutes, the lasagna has cooled down to 150 degrees Celsius. So the thing here is, if we must wait until the lasagna has cooled to 70 degrees Fahrenheit before it is eaten, how long will we have to wait? Okay, so we have the original temperature. So the lasagna is taken out of the oven with an ideal internal temperature of 165 degrees Fahrenheit. By the way, if we are solving this kind of problem, we should be consistent with the unit that we are using. So here, in this particular example, the unit that we are using here is degree Fahrenheit. So all throughout the solution, we'll be using degree Fahrenheit. But you can actually convert this to Celsius. Okay, so in solving this problem, we need to have three sets of solution. We have the initial temperature. Well, of course, we represent that with the T sub O, and that's equal to 165 degrees Fahrenheit. That's the temperature of the lasagna after it has been taken out from the oven, and the lasagna is being placed inside the refrigerator with a temperature of 35 degrees Fahrenheit. Okay, well, of course, our T sub O here is 0 minutes. That is prior to putting the lasagna inside the refrigerator. then we need to have a second set of data also. So our T sub 1, after placing the lasagna inside the refrigerator at the end of 10 minutes, it is being cooled down to 150 degrees Fahrenheit. Okay, so we have your T sub 1 here, that's equal to 150 degrees Fahrenheit, and your T sub S, the temperature of the refrigerator. Well, of course, it is still the same, 35 degrees Fahrenheit, but our T sub 1 here is 10 minutes. Okay, we uh, have taken the lasagna inside the we put the lasagna inside the refrigerator with temperature of 35 degrees Fahrenheit. Then after 10 minutes, it is being cooled down to 150 degrees Fahrenheit. Okay, and then if we want to predict the amount of time for the lasagna to cool down to 70 degrees Fahrenheit, then we will be using the formula that we just derived while ago. So our T sub 2 here, the temperature, okay, is 70 degrees. That is the desired temperature of the lasagna before it is being served, for example, to our guest. So that's 70 degrees Fahrenheit. And the temperature of the surrounding is still the same. That's 35 degrees Fahrenheit. And uh, we want to determine the time it takes for the lasagna to cool down to 70 degrees Fahrenheit. Okay, so that's what we're going to compute. Now, you recall that we derived the formula for Newton's law of cooling, the second formula for Newton's law of cooling, that is T, the temperature of the object at a particular time, and this is equal to your T sub S, the temperature of the surroundings, plus your C e raised to negative KT. Recall that we were able to derive this formula using first order linear differential equation. Okay, so the first thing that we need to do is to solve C, and we can only solve C using the first set of data. And our T here is 165, so I place here 165, and this is equal to the temperature of the refrigerator, that's 35 degrees Fahrenheit, plus C e raised to negative k, and our initial time here is 0. So we replace your T with 0. But if you multiply your negative k by 0, the result is 0, and e raised to 0 is 1. Any number raised to 0 is 1. So 1 times c is c. So we have here the equation 165, and that's equal to 35 plus c. Our c therefore is 130. Now we can use the value of c that we just solved in solving k. So to solve k, we'll be using this second set of data. Okay, our T sub 1 is 150 degrees Fahrenheit, our T sub is 35 degrees Fahrenheit, and our T sub 1 is 10 minutes. So we have here 150, that's T, temperature, and your 35 degrees Fahrenheit, that's the temperature of the refrigerator, plus the solved value of C, that's 130, and e raised to negative k, that is after 10 minutes, so we can replace your t here with 10, so you'll be having negative 10k. Then you have 150 minus 35, that's 115, and this is equal to 130 e raised to negative 10k. Then we interchange the left side of the equation and the right side of the equation. So we have here 130 e raised to negative 10k, and this is equal to 115. We get rid of your 130, so we divide both sides of the equation by 130. So we have now e raised to negative 10k, that's equal to 115 over 130. Now in order for us to get rid of your e, the base, we take the natural logarithm of both sides. So we'll be having ln of e raised to negative 10k, and this is equal to ln of 115 over 130. Then after that, okay, we are left with this equation, negative 10k is equal to the natural logarithm of 115 over 130. So our k now is equal to negative 1 over 10. That is dividing both sides of the equation by negative 10. So we have here k is equal to negative 1 over 10 times the natural logarithm of 115 over 130. Approximately, the value of the natural logarithm of 115 over 130 is negative 0.12. And if you're going to multiply that, that's equal to 0.013. Okay, the solved value of k here might change depending on the number of decimal places that you considered in getting your natural logarithm of 115 over 130. So I preferred using, of course, the value of the natural logarithm of 115 over 130. So our k here is approximately equal to 0.013. Okay, again, this value might change depending on the number of decimal places that you're going to use after getting the natural logarithm of this number. Okay, so k is 0.013. Now we are now ready to solve t sub 2 because we now have our k. So in solving t sub 2, solving t sub 2, we need to have, or we need to use the third set of data. So our desired temperature here is 70 degrees Fahrenheit. Our T sub S, the temperature of the refrigerator as it is, that's 35 degrees Fahrenheit. And then your T sub 2, that's unknown. So we're predicting the time it takes for the lasagna to cool down to 70 degrees Fahrenheit. Okay, so we have already the values, the values that we will need in solving your T sub 2. So the desired temperature is 70, so we write it here 70, and this is equal to 35 plus 130 E raised to, your K now has a value that's 0.013, so you have negative 0.013 times T. So we subtract 70 and 35, the result is 35, and this is equal to 130 E raised to negative 0.013 T. Then after that, we interchange the left and the right side of the equation. So we have 130 E raised to negative 0.013 T, and this is equal to 35. We get rid of 130 by dividing both sides of the equation by 130. So we have here the result, E raised to negative 0.013 T, and this is equal to 35 over 130. Okay, so just like what we did a while ago, we take the natural logarithm of both sides of the equation to get rid of your E, the Euler's number. So we have ln of E raised to negative 0.013 T is equal to the natural logarithm of 35 over 130. So the answer is negative 0.013 T. E is being removed already. Negative 0.013 T, and this is equal to ln of 35 over 130. And then if we're going to input this in our calculator, we have negative 1 over 0.013 ln of 35 over 130. Of course, we need to divide both sides of the equation by negative 0.013. So we have negative 1 over 0.013 times the natural logarithm of 35 over 130. And if we try to calculate this, the time it takes for the lasagna to cool down to 70 degrees Fahrenheit is 100.94 minutes, or approximately equal to 1.68 hours. Okay, so that's the application of first order linear differential equation using that is being applied in Newton's law of cooling. Thank you for listening.